Okay, so in this video what we're going to do is we're going to walk through and solve this logic circuit. So it's very similar to the one we've just looked at, but it is slightly different. The main thing being the gates are in different places. So we've got my truth table up here, which I've just taken directly from the video. And I've also got my circuit down here, and I'm going to once again split it into some different parts and we're going to solve it. So let's make an intermediate point here and we're going to call this D. So very similar as we did before. What this means is we can actually ignore the whole rest of this circuit for now because we're not interested in that. So we're going to look at D and we can see this is a really simple OR gate. So if we work out our truth table for OR, we've got inputs A and B and a single output which we're going to call D. So let's count up in binary, so 0, 0, 0, 1, 1, 0, and then 1, 1, just to make sure we cover all of the points that we need to. And remember, for an OR gate, we're looking at A or B being 1. So to begin with, A or B, 0, A or B is 1, A or B is 1, and our final situation, A and B are both 1, so with our simple OR gate, D is also 1. So what we're going to do now is transfer this information into our truth table. So what we're going to do is we're going to ignore C for now because we're not interested in that, and we're going to fill in column D. So remember what we're doing, the same thing as before, we're just looking at A and B and we're looking for when either one of those or both of them is high. So 0, 0 gives us 0, 0, 0 also gives us 0, 0, 1 gives us 1. Here's another variation of that, so we can see we've got a lot of 1s here. And then finally our AND situation, which is still giving us a 1. So that's column D sorted. So that's half of the circuit done, so give yourself a big tick if you've got that far. Right, now let's look at the second part. So I'm going to delete all of this stuff that I've done so far and give us a bit more space to work. So now we're going to give it so we can look at the second part of our circuit again. And this time what we're going to do is we're going to ignore A and B. And we can see now we've got a situation where we've got C and D giving us our output Z. So let's draw our truth table for our simple AND gate. So here's C and D. Oh, shouldn't have done that. That was a mistake. C and D and our single output Z. And you can see, again, my working is pretty messy, but it's just to give you an idea of the process of how we go through and solve this. So let's put in our logic conditions there and our output Z. So we're looking for the AND condition. So this time we must have C and D high, and we can see that only happens in one situation right at the end. So let's now transfer this information to our logic table, and this time we're interested in C, so I'm going to delete that bit when I crossed it out, but we're not interested in A and B, so I can cross that out now. And this is going to help make our circuit solving a lot easier. And you can see in this example I've actually given myself space with column D, so it makes it much more logical to step through and find the solution. So we're looking for C and D being high. So we can see we've got a 0 there, 0 there, a 0 there, 0 there, 0 there, 0 there, 0 there, and finally we have C and D being high. So that gives us an output 1. So what did this mean? Well, it essentially means that we only get the lamp lighting up in the final condition when Z is equal to 1. And what you can see is, I'm going to delete that bit so we can see, the only condition where Z is 1, I'm going to change colour, so bear with me. Okay, this situation down here, okay? So essentially, we can ignore the whole rest of the table, and this is getting really advanced. If you're not following me here, don't worry. But what this means is we can essentially simplify our circuit, and there's loads of different ways that you can do this in digital electronics. We don't have time to go into all of them here, but if you're interested, basically what we can do is, instead of having this quite complicated system, we can use our truth table to find a simpler answer. And what we have is when A and B and C are true, we get Z is equal to 1. So what this means is, I can delete that because that's just me going off on a bit of an aside, but we could replace this whole system with, this is where it gets cunning, a single AND gate which has A and B and C as inputs and a single output Z. And you can get triple input gates. We talk about double input gates just because it's simpler to work with, but triple input gates do exist, and this is one way of simplification. So we can replace 2 gates with a single gate, and as you can imagine, this would make our circuit cheaper, which is generally what people like. And that's it.